it'll look at my Toshiba, and you'll see it. It'll start doing zone tables, and it recalculates those on the fly. Now, I've got a small drive, and it's a fast drive, so it'll do it pretty quick here. There are some Seagates it takes 24 hours to rebuild that head map. And so basically when I'm done with this, like right now, the whole drive up to this point had just been seen as one big giant space. After this, you'll see there's a where the LBAs are, where it's counting over there. On the left-hand side, there's an H. You see the H? It just added that when we ran this module. Before, it just said LBA blocks. So what that's doing is when it's done, wherever my cursor is, wherever it's sitting on here, it will tell me which head I'm on. So it will actually know, and so you can see I have 4 heads. I have head 0 through head 3, and then these are the zone tables broken up on each side of the platter. And I'll talk about that again so it's clear what I mean. But basically just think of football field, football field, football field, and then that way those are designed for speed. When you get to the end of the football field, if the head that's talking to the drive is faster going to the next platter, it'll put the next zone on the next platter. So it's always about speed, and it'll count down from the fastest zone to the slowest zone. And so it'll recalculate all of the zones based on speed. Now they're already done at the manufacturer's time. Like, it's not like they recalculated it per drive. They've already done all the work for you ahead of time, and they already know the zones are already this fast. And they've organized them according to speed. So the point that I would make here is, so now where my cursor is sitting is at head 0. So if we're talking about zones, the important factor is this. You don't have to worry about the speed of where the zone is because the drive has already figured it out. But when I have an argument with somebody about hard drives, it usually comes down to this, especially somebody who thinks they know something. Some forensics guys over there, wherever, that teaches other things. Several companies that teach forensics that think they know something, or maybe somebody like Brian Carrier and Brian Carrier's books. They just don't have all the information, let's put it that way. In the olden days, when you would write to a drive, you would have a platter sitting on top of a platter. They are segmented through a cone, right? So you have this cylinder, and whatever it wrote here, then the next block is written here, then it comes to the next side of the platter, then the next side of the platter, right? So that's how data was written when it was CHS. That is not how it's written now. So now what happens is you have 2 platters. Now this part right here is going to be zone 0. So that's the first zone. It's a football field of data that goes around the outside edge of the platter. And so that will now be a speed. They will calculate a speed, and it will be 10 milliseconds or whatever it is. Now when the head gets to this spot, it now takes longer to read this section than it does to go to the outside edge on the bottom of the platter. So zone 2 or zone 1 would be out here, and that might take 12 milliseconds, or so on and so on and so on. So they organize them according to speed. So eventually you'll get through all 4 of these edges like this. And so the effect is your head on your outside edge of the platter will go that far, then you will see it come back again. Then the head will go that far, then you'll see it come back again. Then the head will go that far. It'll do it 4 times, for however many platters you got, for how many heads you have, you'll see that head do that many times as it reads the data and images it. Then it'll go to that end where it just was, and then it will go the next piece. And then it will do that 4 times. Then it will do the next piece 4 times. So you get my point? Everybody get where I'm going with this? So when you're looking at how the heads work, that's functionally going to be a difference now in how you're looking at the data versus this old method where you would just write data down segment by segment through all of the drives. That we haven't done that since the late 90s. So from 2000 and on, we started with what's called LBA 28-bit mode, and we are currently at what's called LBA 48. Oops. No. 48-bit mode. So that's where we're at now. This happened around 2000. We switched from LBA 28-bit mode around 2002 or so. That was a BIOS upgrade that had to happen on everybody's computer or everybody's card. It actually was 32 bits, but 4 bits were reserved, so they call it LBA 28-bit mode. And this was actually 64 bits, but then the 16 bits or whatever it is, this flag is reserved, and so it's 48 bits. We can only talk. This part right here, LBA 28-bit, we had to move from 28-bit to 48-bit when we got a drive larger than 137 gigs. So that's the number, is 137. Once we got past 137, we could not talk to a drive. There's no drive made that's 137 gigs. We had a 120 gig drive. Then we had the 160 is actually now perpendicular. That's a different type of drive once you get to that far. Then we had a 160, and then we have 200. So 200 is in the original spec before we got to the perpendicular drives. So this was around 2002, 2001, something in that range, and then we switched to this, and now this will let us go. So far we haven't reached the limit. It's the extent of our drives currently from a physical size. I don't know if we'll have to change by the time anything else happens. They've decided instead of changing configurations, we've been looking at 512 bytes all this time. They are deciding for us that we're going to increase that by a factor of 8, and our size will now be 4K, and we are not going to be at 512 bytes anymore, but it will currently kill us. It currently will crush everything that we have. It is already out. It is already running. It is already in forensics cases, and it is just rare because it's all enterprise type equipment. And so the day is coming. Axiom currently does not run on it at all. Axiom based on IEF is hard-coded to 512 bytes, and so without it being a real 4K, they've said that it will take them a year to do a rewrite to get that piece of code. And I don't even know if they actively took it up yet. It crashes. It won't even work. It doesn't even run on the new cases. But there will be a lot of things that don't run. The only one natively that actually works, natively, is X-Ways. The X-Ways already, and part of this is because me and my partner in Australia test all of these things, and then we call Stefan and tell him. So Zoran has been feeding stuff to Stefan for years to fix problems and do stuff, and he is a very exacting guy. So he's got a very, when he tells you there's a problem, it's a real problem. So, all right, I know we're getting late here. All right, so this was supposed to be all about firmware, so I'm going to skip ahead a little bit because we're going to come back to the Atola stuff because it doesn't really fit in the firmware category anymore. I hate to pass this slide. All right, here's where the rubber meets the road. All right, so here's the thing. I'm going to ask you a question and you tell me what you think. So this is a media scan. The Atola decides in its beginning process that it's going to test the drive by doing a media scan. It does some for you already, and then you can manually do the whole drive if you want to. It doesn't image or do anything during this process, so it's kind of a detrimental process to do while you're not imaging. But it gives you a presentation, a layout. What page are we on, you know? Anybody know where I made it to? 172. All right, so here's my problem. In my mind, when I look at this, I'm just going to try to give you an idea how I think in this process. So I get a media scan and I look at this. And without the Atola trying to tell me what's wrong or anything else happening, what is wrong with this drive? Anybody have any idea what's wrong with this drive? It is a bad head. How many heads are there probably in this drive?
3.
It's 4. Yep. 3 is close, and I can see why you got to 3, but if you look at the breakdown, and so I'm going to visually show you what I mean. So if this is a bad head, then you've got basically from this space to this space. Now you'll see that there's another head that's being affected. You see where the beginning and the end is? So you can see this start to happen, and it's repetitive. So it starts to happen, and you can see this head is getting affected. This data is taking longer and longer to read, and it's physically going to die. It's going to die soon. And it's probably because whatever's on one side that scraped the platter means there's media damage and material is coming off and it's scraping the other head. And so by looking at a picture of a media scan without ever opening the drive, I can guess that's what's happening. Okay? So I know that side of that platter is scratched. Right? That's the first thing that I come to. That's the first conclusion I would have by looking at this based on this picture. And I would hope I'm wrong, because obviously that would limit my recovery process. But I'm hoping I would be able to change the head of a drive and be able to get that working at some point and read something. But that head is definitely dead, and something has suffered on that. And these are multiple areas of the drive that it is reading across different heads, right? So those are zones. Those are big giant zones as it's going down through a stack. And there's four heads, 2 platters. Everybody good just by looking at the picture? You good? All right, so now that means these two. So that means these two right here might be doing okay. So, but this is where my detriment starts. So now my next question would be, well, crap, how bad of a recovery is this? And my first thought is, I don't know. Shoot. Dang it. Stop. That's the only bad thing about this. So I'm going to try to zoom in so you can see here. So these are the sectors. You can see this one starts at 0. This is 409, 600, 819, 200, and so on from here. Okay? Now, if the question is, what if I just turn off this head, leave it off, and image the drive, and I get lucky enough that I can get even that one before everything dies, I can get that. That means I got 75% of the drive. Right? Now, data is contiguous in chunks, right? So when I'm saying this, what I think is, well, and this is a problem I always have with the argument with people, is that as data is written down through the drive, they think, well, if I turn off a head, well, then I'm missing part of a Word document. Like they think every other piece of a Word document will be missing. Well, no, it won't. It's contiguous data for a chunk. So let's say that this is a 2 gig chunk or whatever. And in that 2 gig chunk, I happen to find the My Documents folder. And in the My Documents folder, as far as Word documents go, I mean, obviously we have got big stuff. We got photos and videos and pictures and things like that. Those things are all going to be big stuff. But the small stuff are these 79K Word documents. Those things will come off complete. Because wherever I find a chunk, and a contiguous chunk, then 2 gigs or 6 gigs of whatever it is on that side of a platter is going to be contiguous. And as long as I've got a pointer that tells me the metadata, I can get the folder and all the structure for all of that data, right? NTFS, the Windows file system, stores everything about every file or every folder in 2 sectors. So every sector, every 2 sectors for this entry is all it needs for metadata for everything about a file that exists. Does this make sense to everybody? So this might be new to some people, but you have what's called the master file table. The master file table is a stroke of genius. It's literally all you have is record by record, 2 sectors, 512 bytes each, so a total of 1024, and it has all the record data, as long as it's not a run-on, it has all the record data that you need to know about an individual file. Does that make sense? So if I have that record, even if none of the other records survived, if everything else was dead, I could find the one record, the pair that goes together, then I could go find that file, and I would have the name, the date. I wouldn't have the parent wouldn't exist, but the pointer to the parent would exist. So you'd have what's called an orphaned record in some way. And so what that means is it no longer knows what folder it belongs to, or it knows the name of the folder in many cases, or an ID for the folder. It does not know where it belongs in that folder anymore because the folder doesn't exist. Does that make sense? So now I have a record, I have file name, date, time, everything about it except for that parent folder information, which is stored someplace else. So I'm good. So if I had an NTFS set of records that starts at the beginning of the drive and it was somewhere around here, and I had a record, everywhere that's green that survived, in the hopes that if I never can get the red stuff back, I can find a good record and it will survive. Does that make sense? Everybody happy with that idea? And so because those records are all individual, even if this chunk is bad, whatever MFT records I have over here, or maybe MFT records that exist somewhere else, or maybe another partition over here, I can read that file and get it back. Okay, I've said it many times now. Everybody happy, right? FAT. So if I start going through the file systems, because let's say I don't know what the file system is right off the bat. So that's NTFS. As long as any piece of that exists, I'm happy. FAT has two tables. As long as one of those tables survives, then it points to the cluster list, and the cluster list is going to be directory to directory. So, and whatever that chunk is that's inside the directory, I could probably find, link all those clusters together and survive. Or I could do it automatically with some software. There's ways to do that. But so if the FAT tables, they exist towards the beginning of the drive, so they're probably sitting over here somewhere. And whatever records I have that exist, wherever it points to that's green, I found something that survives, right? So I'm pretty good with those two file systems. Linux, which would be, okay, this might be a NAS box or something like that. Linux generally is going to be using ext3. There's also ext4, but that would be solid state, so we're not in a hard drive, so I'm probably on a real ext3. ext3, anybody know anything about Linux and the file system? What does it have that none of our other file systems really have? Journaling. Has what? Journaling. Well, we do have journaling even in Microsoft's, even in Windows. Transaction-oriented file system is the exact same thing as journaling. They just call it Microsoft's name instead of the journaling name. But so we do have that. We have it in Mac, we have it in Windows, and so we also have it there. But what they have in their file system that we don't have in any other file system is a redundant table. NTFS, only that MFT table only exists in one place, and only one copy of it exists. There's an item that's called an MFT mirror or an MFT copy, which is a lie. It's a copy of 4 pointers. That's all it's a copy of. The same 4 pointers that one of them is itself. It's redundant to itself, so only 3 of them are important. So outside of that, there isn't any other records that exist that are important. They're just a copy of the pointers to the beginning of the tables. In case that sector dies, that it can go find the pointer in the middle of the platter, in the middle of the partition, and come back to it. Okay? So as we're going through file systems, does that make sense? Okay. So ext has a redundant table. It actually uses something, it's called magic numbers, and it creates a new table, and there'll be a new block cluster group, a new cylinder block cluster group that will exist several times throughout the drive. And as long as you can find any of those by looking for the signature of that block, wherever that table exists, you can then use that table to point to wherever the other files are. This redundancy has actually caused it quite a bit of problems because now drives are so big, it takes a really long time to update that table. It's a little bit like the Vista problem, which is why ext4 exists to fix that problem by removing redundancy. So they remove some of the redundancy. However, that's the whole point, is that it is redundant. And so anywhere that I look, I can at least find these tables that point back to where the files exist. So even in a situation like this, with one head dead, I've got stuff I can recover. Now, HFS, Max File System. What does HFS stand for? Anybody know? HFS. Not HPFS, that's the high performance file system, which is NT. HFS. Hierarchical file system. And what does a hierarchical file system look like? What do you think a hierarchical file system looks like?
It's a B tree, isn't it?
It's a B tree. And in a B tree, what does a B tree look like? Nobody? Here's what a B tree looks like. I don't know wherever we have 2 vice presidents, but maybe we have 2 vice presidents of 2 divisions or something like that. So it looks exactly like an org chart. This is supposed to say plebeian. So basically, that's what it looks like. The root of the tree starts here and then branches, and then it wear levels itself and then constantly keeps adding to the tree, and it's a org chart. It is your standard corporate org chart, fall down the whole tree, and it levels itself. It's always at the same level. So there's never like a branch that has like 20 other people. There's always a level, and they're always the same. So this tree always looks like this. Here's the downside. What happens if I shoot the CEO? What if I shoot the CEO in a hierarchical file system? What happens to the rest of the data in the tree? Nope. You can never find the branches again. They are lost. The entire tree gets knobbed off. So in a B tree structure, it's very difficult to find the next following structures. So if once you've lost the root of the tree, there are some rare rudimentary tools that I've had for like 20 years that can rebuild parts of the tree and find a branch and then try to rebuild a portion of the branch. But typically when you have a sector failure, or you've got some sort of problem that happens, it kills the rest of the tree. You have no table, and it's hard to find all the stuff. It's completely lost some of its organizational structure in the process of trying to rebuild it. So it becomes extremely difficult to rebuild these trees. So all the other records that we have all stand alone. Everything else has a standalone process, and you can find them and rebuild them. Not HFS. HFS is a real problem, and this is why Macs can't even fix their own problems when something bad happens. If they can't rebuild the structure, they can't find part of the structure, they just die on the vine, and you can't rebuild them at all. So all you're left with is, if you can't find a binary tree reconstruction tool that will work, then you have to carve all the rest of your files. Now there's a good side and a bad side. The good side is Macs defrag themselves 3 minutes after the system rebooted. So any file that's 20 megs or less is automatically defragged all the time. So the photo library is contiguous all the time. And the only people using Macs care about is photo library. That's all they care about. They don't care about anything else. There's nothing else important in their entire life except for their photos. And so you can go carve all the photos, and they won't have names. So what? I mean, you could probably find some EXIF information and parse it out, but other than that, there's the names. Every one of those JPEGs might have a name. They may lose their videos. There may be some problems there, but ultimately, in a chopped up version like this, that's what you're dealing with. Now, I'm going to go back to this picture for a second. Here's your biggest problem. If this was a Mac, the partition structure starts. I just happen to know this. So this is why I look at things, and now you will know this. The partition structures for Macs, there's like 4 partitions, and one of them is after they get past the patch partition and the boot partition and the other stuff, the first one is the partition that has what's called the catalog. The catalog is the equivalent of the master file table in Windows. It even looks almost identical. There's a lot of stuff that's the same inside of all of those. But the catalog and the root of the catalog, where the CEO lives in that process, starts at 409.642. And guess where that is? There's 409.600. 409.642 is right about there. So the root of the catalog in this picture is dead, right here. So I know without the rest of that right there that I lose the catalog, and maybe I get lucky and there's a couple records I can retrieve, but the majority of my catalog is dead. So I know in a Mac, I can do everything I want, but I'm not going to get that data, and this is going to be very difficult. I'm only going to be able to carve out JPEGs and video files and hope that I can get something back. But a Mac person wants everything, their file structure and all this data, like they're very particular about their layout. They may not be happy enough to pay me for a recovery. Does that make sense? Now, if I find a dead picture of grandma that had expired 20 years ago, I probably will get paid. So I usually look for that. I look for like dead relatives, old relatives, funerals, and then I make a contact sheet and I email it to them and say, I found some pictures, what do you think? And then, oh yeah, I remember grandma, and they pay you. So that's kind of how that goes. But I'm just going to point out, without another head or trying to get this platter working, I've got a real problem on this drive. But that's how I think. I immediately go through all of this in my head. So the next thing I would have done is gone to the boot sector and looked to see if this is a Mac, Windows, or something else. And so I'll show you as we're going to go through that tomorrow. But fundamentally, that's what I'm looking at. This is a real zone table. This one was pulled off of a hard drive. The entire point that I'm trying to make is those little football fields are actually contiguous data. You can see the start LBA, the end LBA, so there's a count for the LBA blocks, and you'll see that not only is one of them contiguous, like there's 3 that were fast in a row, so the entire spectrum from 0 all the way down here to 12,832 is all contiguous data. It's 3 zones added together, but it's all contiguous. So I got 6 gigs of data that I can read all at once from that standpoint right away, if that makes sense. So I can go through this kind of process trying to determine how much data I'm going to be able to get in the process. Does that make sense? Everybody happy with this? All right, so tomorrow we're going to talk about the DeepSpar stuff. Atola, DeepSpar, and PC3000 all do imaging. We're going to ignore the rest of this. But we will definitely be going through that. I've already talked a little bit about passwords on drives and that you can have a password on a drive. And there used to be ways to clear these passwords using software that is no longer available anymore. You can't do it anymore. The only way that you can clear them now is to have a hardware tool. So the Atola has built-in functions. When you pay for the Atola, it actually comes with it already. The PC3000 also does it right away. Even in their $4,000, there's like a $4,800 version of the PC3000 that doesn't have all the add-ons, but it does do passwords by default. The DeepSpar, you have to pay for a tool that they add on. The DeepSpar has something called the Disk Wizard or the Drive Wizard or something, and so it is right here. Unlock password. Unlock password there's a user password and the unlock wizard. And so it has to know the drive, so you would hit this and it would say, okay, I got these drives and I want to unlock a drive. And it'll try to erase the password in order to give you access to the password. There's a problem. Only the PC3000 does IBM Hitachi drives, which are now Western Digital Hitachi drives, because the design that IBM had for those drives locks the system area, and you have to short the system area with a fuse in order to get to it. So there's pins on a board that you have to short, and then you can get access to it. So the IBM Hitachi drives are the only ones that you would have to go to and figure out, and you need somebody to tell you which pins. They're not the same pins every time. So it's the only one that does them. This one is pre-IBM. So this Hitachi one is pre-IBM. That's why you don't see any of the others in the list. And then in updates and stuff, sometimes they add other stuff. Because Seagate used to be in here, but there must have been a problem and they added some new stuff as they go. But theirs is very limited. I would way prefer either the Atola or the PC3000 to do passwords if I was going to do it. But all this does is get access to the drive that is locked. It doesn't solve any data recovery problems or anything else. But sometimes that's what people think the data recovery problem is. I've seen that situation where the Geek Squad comes in to a CEO's office. He wants to upgrade. He was using a biased password, but the dude pulled his hard drive out, plugged it into an external unit, plugged a new hard drive in, installed Windows on it, and then he was trying to copy over the guy's data but never could get into the drive, and then doesn't realize that that's all it was a password, so they send it into recovery. So they just completely screwed up right away by not knowing it was a password or looking to see if there was a password on it. So all I got to do is clear the password and send it back. And $800, baby. So as quick as I can. All right, so, but I did list some software and stuff that no longer exists. The Atola actually brings up like a box, a security feature box, and then shows you, and then you can pull up the password and you can see it. So, you know, super secret password. And I don't even know if the Shinola box still exists anymore. It was a password box that was created by the same people. Like Dimitri was involved in the process of this, but I think it's obsolete at this point. So now these are too complicated for us at this hour to discuss right now, I think. This is the next thing, and this is what we'll cover in the morning, and that will finish up these few pages that I have right here before we start getting into the rest of the drives. But there are these are IDE specs. These are ATA and IDE specs that happened and are applied to all the drives. These are all the drives all the way up to and including LBA 28-bit and then 48-bit. And there are some commands that we're going to use in data recovery with the deep spar that are important, and they're for all of them. It doesn't matter. The commands are the same. But you need to kind of know why and where we're going to use these particular items. There's 4 of them that we use as a whole, as a setting, because every spec of the ATA commands adds or removes compatibility with something that previously existed. And they did add and remove something at ATA 2, and then they went to ATA 6, where we had to change how we read drives. Remember, I told you a few minutes ago that up to LBA 28-bit mode, we could read 137 gig drives. And then we surpassed that somewhere in 2001 and 2002. But then, eventually, we went to LBA 48-bit mode from 28-bit mode. And then that's what we're currently on. 48-bit mode at ATA 6 is where we currently communicate with our hard drives with 48 bits. And so, basically, you know, we can figure out that's how large that is, but it's a pretty large set from a standpoint of the number of drives. So, the thing is, when they went to LBA 48-bit mode, they decided we no longer need a command that we had when we were in LBA 28-bit mode. There is a command in here that is called ignore ECC, or known as a read long. So those two things are very important. So if we can ignore ECC, we can read sectors that would only return 0. So I'm going to try real quick to describe this and see, and then we'll leave HPA for the morning. So in your sector, there's 512 bytes. There's way more in a sector than this. I'll actually show you a real sector. There's a whole bunch of stuff that's there and there. And then right here at the end of 512 bytes, there's 4 bytes called ECC. And this is the error correcting code that says, if I compare content coming from 512 bytes, can I tell if the drive read it correctly or not? Did the head read the data correctly? If the head did not read the data correctly, I can try to repair it with the ECC content that's right there. If that does not work, tell him it's an error and give him 0. We don't want to give him a guess, so we give him nothing. So if you're using Encase or FTK, or you're copying this even with another tool, you're copying a hard drive, when it gets to the error, the reason that your stuff is crashing or doesn't continue on or make a copy is that what it returned is 0 and said I had an error, and it just quit. Encase and all these other tools don't even know what the error is. There's actually a real error. It actually reports the error to you and says I had an error because of this reason. And there's a whole set of control flags and status flags and error flags that it tells you why it failed. And our data recovery equipment will normally tell us what it is. But Encase and all these other $7,000 worth of tools do not tell you anything. You would think they'd work on that part a little bit, but they don't. They don't care about the imaging part at all. It's nothing but a dumb version of DD. And there's a little bit of granularity, and there is a little bit of I want to pick back up where I left off. But that's all that there is. There isn't anything else to deal with an error that actually occurs. In hardware, we can tell the drive, I want you to pretend that you're in 28-bit mode as long as the data is in the first 137 gigs of the drive. So normally when you power up a drive, it says, I support LBA 48-bit mode, and it will go into the highest mode available. And it will also say, well, I support ATA spec 6 or 8 or whatever's available for the drive at that point, and it will immediately use only that command set. So you have to tell it, I want to go back to 28-bit mode and use ATA spec 2 in order to use an old command. And as long as the drive still has code in it that supports that, we can get the data back from the drive without the ignore ECC. So here's the whole point. You say read, it reads this, oh, there's an error, I tried to compare it with ECC, it's wrong, give him 0 and quit. So I say, no, don't quit. Pretend you're in LBA 28-bit mode, re-enable this old command, and read the 512 bytes and ignore ECC. Don't use it at all. So just ignore it. So it doesn't matter what it says. So that means whatever data you get back from the drive is wrong, but you got data back. Does that make sense? So now, here's where the DeepSpar is one step better than all the other tools. Eventually, Atola is going to implement this. Dimitri has told me, he's promised me he's going to add this, but he has not currently added this. The DeepSpar builds an array and rereads that sector as many times as you tell it you want it to reread it. I think the maximum is 99 times. So you can say reread that sector and populate an array. And then reread it again and give it another 512 bytes and keep adding to it. Every time it reads, it compares the previous one, the previous answer, and it does a bitwise comparison. So not just bytes. So because normally when you're talking about bytes, there's 8 bits in a byte, and you have 512 of those. So rather than saying I got an 08, I can look at another one and say, oh, I've got more than an 08. I got these number of bits that are identical. So at 50% it falls out. Does this make sense to everybody? So every time it compares, it looks at the last one and says how many are the same, and makes a new row with the same. And then how many the next time are the same. And it keeps adding those up, and so it knows that 50% of the time, if all of these bits are the same, let's keep those, and then we keep reading until we get a really good read. Does that make sense? So I'm building an array rather than taking one bad guess. I'm taking 99 bad guesses and adding them all together, and wherever they look basically the same, I'm going to keep all of that. Turns out that's right most of the time. It's significantly right. Enough for files to work and JPEGs to look fine and videos to run and things like that to happen. So we have a process that fixes some of those things where corruption in a big file like a video really makes a difference by doing this, especially on drives that are older drives. So a lot of the drives that are older drives all started with ATA2 as their support, and even when they added on to that, it was ATA2 for many years up until it became ATA 48-bit in ATA6. Does that make sense to everybody? So I have a chance at reading some sectors that Encase and FTK and DD and all these other tools cannot do, that I can do on a DeepSpar, and I can do it better than any other tool that's out there. And so if I have that situation where it happens and I'm in a court case and I have an option to take that drive and run it through and ignore ECC and read all the ones that didn't work on a DeepSpar, and then we go to court, and right now, if you used Encase and you image a drive, you guys doing that, right? Yes? And you get a bad sector, you get padded zeros, right? You're going to go into court and you're going to testify and you're going to say, well, there was these 12 errors, and so there's 16 sectors I did not read, and the guy's going to say, hey, well, what was in those 16 sectors? And you're going to say, I don't know, that came back as 0. And then he's going to say, was there a chance that there was exculpatory information in there? Is there something that says my client is innocent? And you're going to say, well, I don't know. They were 0. And then he's going to say, well, is it possible that one of those sectors said, I am innocent? I'm not kidding you, that's what I say, because the jury's hearing, I am innocent. Is it possible? And you're going to have to say, yes, it's possible. And then I'm going to sit down on the stand, and I'm going to say, I read all of those sectors. They came back using ignore ECC as a process, and of course the jury's not going to hear it. They don't ignore ECC, who gives a crap, whatever. I don't even know what that command means. And then they're going to say, so did you read data? Yes, I did. I read data. What did it say in it? It said, I am guilty. And so, or whatever it is, whatever is in that sector. But the point is that you got 0 and I got something. And that builds credibility in that process with the jury. So it doesn't matter what I got or what is right or how right or wrong it is. I'm going to say it's an educated guess, and this is what it looks like, and here's the picture. And show you a picture, and you're not even going to be able to tell that there's a blur that's missing or whatever else. It'll look fine in a JPEG. Does that make sense? And so that's my entire process. That's like 99% of what I do every day, is I try to use ignore ECC, and I try to recover those sectors, and I try to rebuild the best possible guess after I've whittled down all the other choices. So it's my last kind of shot at getting sectors nobody else can read. Because If you only have a couple of sectors that you can't read, that's the only thing you can do. Realigning the head, replacing the head's not going to work all day long. It'll never work. And you don't know for sure that the error isn't in the ECC. If there's an error in this sector, and this part of the sector is damaged, this part, I mean, it's unusual, but this part may be fine, and whatever it's reading here is wrong in these 4 bytes. And so those 4 bytes they come back and say, oh, I'm sorry, I don't have a good answer for you, so I quit. So I get an answer. And you can see it. You'll see it when you're doing it in the recoveries. You'll see it like update on the screen, because there's this little hex editor that basically runs while you're imaging. And so I don't know if any of you have seen this, but so while this is imaging, you can have this little hex editor that's running, and when it's focusing on one sector, it'll constantly reread that sector over and over and over again. You'll be able to see the same content building as it goes. I mean, sometimes you'll be able to read it. Sometimes it'll say Microsoft Windows, girl in red dress or something. You'll be able to tell that that's exactly what it's doing, and eventually you'll see characters flip, and then all of a sudden it'll say the word and go on from there. So it depends on what it's reading and what you're looking at when you're in that process. But I can tell a lot by looking at what's going on in the screen. This used to be bigger, and I'm sad that it's as small as it is now. But they've added some other things, so you can see, like, here's all the sectors I'm imaging in my big map, and here's my individual location, and here's my speed of all my heads, and how long is it going to take. So there's a few of these things that they have added over time to give you more feedback in DOS, but and so I lost some of my, because I used to read them and literally say girl in red dress. There's some JPEGs going by. I could tell this is an apple. So you can see those kind of things. All right, so that's what I have for tonight. Tomorrow we'll come in, we'll finish a couple of slides here, and then we'll move into the day 2 stuff, okay? Everybody happy? All right. See you guys at 6 a.m. Traffic will be a bear tomorrow. It won't be a holiday.
Can we leave our books in here too?
Yes, yeah. The room will be locked. Everything will be locked in here.